Well, hello everyone. My name is Siyi Xu. I'm an astronomer at Gemini Observatory, NOAA Lab, and I'll be chairing the next session, Stellar Evolution and Planet-Star Connections. And our first speaker is Luke Bouma, and he's giving a review talk. And the topic is Know Thy Star, Know Thy Planets, an observational view of exoplanet environments and outcomes. I will give you a 5 minutes reminder. Thank you. Yeah.
Okay. Lovely. Much better. Thank you. I'd like to thank the organizers, not only for the chance to speak, but also for bringing us together. Putting the solar system into context is a pretty big goal. I think we can all agree. And we need to have meetings like this if we're going to make it happen. Many. So today, I've been tasked with telling you a little bit about star-planet interactions and stellar evolution. I'm an observational astronomer, so I decided to focus observationally on what we've been learning about how stars influence their planets. And if I had to leave you with one message, it would be a mantra that I imagine many of you have perhaps heard already. Know thy star, know thy planet. Okay, what does this catchphrase mean? Today, I have two specific meanings that I want to highlight. The first is physical, right? Physically, especially for close-in planets, stars can alter the planet. The second is observational. In exoplanet science, we have a menagerie of indirect methods, transits, radial velocities for studying the planet. We also have direct imaging. Really, regardless of what methods you use, you should understand the shiny thing that you're observing at least as well as the faint thing that you're trying to study. Okay, so know thy star, know thy planet. But for which exoplanet outcomes do you need to know thy star the most? This is a dependency matrix that gets at that question a little bit. Okay, so how do you read this? Well, oh boy. Let's say you want to measure a planet mass. There are a couple things that are going to matter, both observationally and physically, for doing that. So for example, observationally, if you want to measure that mass using radial velocities, you had better know the star's mass. Okay? Physically, I'm going to argue today that if you want to be able to predict a planet's radius, its size, you need to know a couple different factors. Its age is one that I'm going to highlight. Conversely, let's say you're interested in orbital architectures of planetary systems. As far as we know, the stellar input of, say, the wind probably doesn't influence that very much. Okay, so the point of this plot, we're not going to go through every cell. The point is that there are many areas with at least some dependence of an exoplanet outcome on a stellar input, if not a strong dependence. Okay, so for the next 20 few minutes, what I'm going to do is I'm going to talk about the exoplanet outcomes that I think are most strongly dependent on a stellar input. So we're going to start with the classics. Okay, the first one, stellar sizes. So we've seen the radius valley already. I won't rehash too much of it, but one aspect of this measurement that I want to highlight is the importance of the stellar size measurement. So from the transit method, what you measure is a depth. If you want to measure a planet size from that, you need to multiply by the stellar radius, r star. During the main Kepler mission, so the early 2010s, the stellar radii were uncertain at the level of like 30, 40%. So the size distribution was a blur. A couple groups went and measured high signal to noise, high resolution spectra. And then the radius distribution that was measured separated into these two peaks. A peak of super Earths, a peak of mini Neptunes, aka sub-Neptunes. I think mini Neptune is a little bit cuter. And the fact that they separate in size distribution tells us that they have different interior compositions, right? The mini Neptunes have some kind of volatile component. The super Earths, by size and by mass, if they have any volatile component, it's much smaller. Okay, so that's something that stellar radii taught us about exoplanets. But what does that say about the solar system? Well, from the exoplanet surveys, these are the most common types of planets currently known. The solar system doesn't have any. So what that tells us is that at least a third of sun-like stars are different from the solar system. Okay, so that's the first classic, stellar sizes. Going way back, stellar metallicities were actually first. So stellar metallicity, the amount of iron that's measured in the photosphere relative to hydrogen. The Geneva group, in their initial radial velocity surveys, noticed after a while that they were detecting more giant planets. Cool giants, Jupiter-like planets on wide orbits, also the close-in ones, the hot Jupiters, around metal-rich stars. And the dependence is strong. It's roughly quadratic here, in this work led by a team in California. Since this early pioneering work, we've been able to extend these studies using, for example, the transit technique to study how different types of planets depend on stellar metallicity. So how does the occurrence of giant planets, great, the mouse is here, so the giant planets close into the star and a little bit further out, but still within orbital periods of 100 days, how does it depend on metallicity? So the giant planets are rarer. Those are the red and the orange lines at the bottom. And the mini Neptunes and the super Earths, they're much more common. But if you look at the slope, right, the slope is steeper for the giant planets than it is for the mini Neptunes and the super Earths. And that tells us something about the mass budget that's required to form a core that can then undergo runaway gas accretion. People have gone further than just iron. There have also been studies using high-resolution surveys like LAMOST, in this case apogee, that look at whether it matters which rock-forming elements you use to create the core. So this beta parameter that I'm showing here, that's the slope of the occurrence to metallicity correlation. Okay? And basically what you find is that it doesn't matter whether you talk about iron, magnesium, silicon. The dependence of occurrence on rock-forming element abundance remains the same. Okay, we've got stellar radii, stellar metallicities. I'd like to spend a little bit of time talking about a third stellar parameter, which is ages. Before I do that, a point that I almost forgot, and it's an important one. The solar system is in a minority in terms of its giant planet population. 10% of sun-like stars have Jupiter-like planets, but we have Jupiter and Saturn. So the conditional probabilities are actually still, I would say, a little bit shaky. People have looked at it using long-term radial velocity surveys, but it's certainly the case that if Jupiter is 10%, then adding an additional giant planet is going to lower the conditional occurrence. Okay, ages. So, oh, it's not advancing. It's now advancing. So stellar ages are hard to measure relative to sizes and metallicities. We have like this large set of different methods that work for different types of stars at different evolutionary phases. And I am nonetheless optimistic about what we can learn from stellar ages because they have the potential to teach us what an exoplanet evolution timeline looks like. So for stars, we've known for like 100 years, right? Given the mass, given the metallicity, given the age, what is the evolutionary state? For exoplanets, we don't have that mapping yet. We're still working it out. So we do have some general theoretical ideas. Early on, the disk is present, cores form, primordial atmospheres accrete, Maybe disk-induced migration causes them to move around. Once the disk disperses, there are then a huge set of other evolutionary processes that happen. So personally, in my own preferred nomenclature, I divide these into the formation era and the evolutionary era. Now, empirically, observationally, it has been very hard to study stars younger than, let's say, 10 to the 8 years. And that's because they're rare. Okay? The galaxy is 10 billion years old. The age distribution is roughly uniform. That means that only 1% of stars is going to be younger than 10 to the 8 years old. So a lot of the early work focused on the older section. After a billion years, what happens? The answer is not that much, at least as far as we can observe. Okay, if you look at, say, mini-Neptune sizes as a function of time, these are model predictions on the left and the data on the right. There's something like a 30% predicted size change from thermal evolution only here. And it's not observed in the data, which might be because the measurement precision isn't quite there, or it might just be, I don't know, we don't have to get into the details. The upshot here is that you can only conclude from this that large mini-Neptune size changes finish within about a billion years. More recently, data from NASA's TESS mission have enabled the discovery of a whole bunch more transiting planets. We heard that the total count from all exoplanet surveys recently passed 6,000. This plot focuses only on the transiting planets. And then I've gone a step further, and I've shown only the stars that are younger than a billion years with precisely measured ages. So there's a whole bunch of selection functions or observational biases that go into that, right? The transit method isn't sensitive to planets far out. In stellar age dating, if you want a precise age, then you're biased towards stars in star clusters, and those have some dissolution time scale, maybe 10 to the 8 years. So nonetheless, what's exciting, I'm able to make this plot today, and if I had made it, say, 5 years ago, the population size would be maybe 20% of what we have here. So we have some detections, in particular, of young transiting objects that are large. Okay? Here, many of them are between 4 and 10 Earth radii in size. What are they? Well, one idea is that they could be mini-Neptunes, so objects with masses of order, let's say, 10 Earth masses, with primordial hydrogen-helium atmospheres. Theoretically, if you assume a very simple interior structure model for mini-Neptunes, like seriously cartoon level, right? You have magnesium silicates in the core, only hydrogen outside, and you evolve that under the effects of external photoevaporation from the star and the internal core power luminosity. Then, stepping forward in time, the overall size distribution tends to shrink, and the objects at the bottom lose their atmospheres and become stripped super-Earths. What I'm excited to report is that from transiting planet studies, occurrence rate studies, this is work led by Sydney Vach, who is a graduate student at the University of Southern Queensland. I was on this paper. We have evidence that young mini-Neptunes are abundant. So in other words, we have an overabundance of these large planets relative to what we would expect in older planet samples. It's not 5 sigma, it's like 3 or 4, depending on how you dice it. So it's only suggestive at this point. More work remains. Nonetheless, I think that what we're seeing in the data are consistent with these objects being puffy Neptunes with primordial atmospheres. And part of the reason for that is coming from a set of independent JWST programs that are measuring transmission spectra for these objects. So you might have heard in exoplanet transmission spectroscopy of the flat line problem. These data are not flat lines, right? You have these whopping features from carbon dioxide absorption, water absorption. And to first order, yeah, you can learn something about the chemistry of the atmosphere from this. But what I'm excited about from these types of measurements is much simpler. You can actually learn something about the planet's mass. Okay, so for young planets, measuring masses is like I don't know how to describe this problem, pie in the sky or the holy grail. The stars spin really fast, they're covered in spots. So the Keplerian reflex semi-amplitude, this really small signal, is dwarfed by stellar activity. It's a very hard measurement to make. Much easier to measure a transmission spectrum. And from the transmission spectrum, the amplitude of these features tells you something about the scale height in the atmosphere. And the scale height encodes the planet's mass through the surface gravity. So if you model these data, you basically find that these objects with sizes comparable to Jupiter have masses an order of magnitude lower, 20 Earth masses, rather than 300. Okay, so that's one thing that the young transiting population is showing us. It's that basically a picture for primordial atmosphere accretion is generic across the solar system and exoplanet systems. There's another interesting result that I want to highlight. We heard about this yesterday. This is work led by Fei-Dai. If you select transiting planet systems that have multiple transiting planets, and you ask, what fraction of those planets are near period commensurabilities? So for example, the innermost planet goes around 3 times, and the planet one further out goes around twice. Then you find that the fraction of planets that are in that type of resonance, irrespective of whether you basically count different types of period commensurabilities, that's the difference between the blue and the orange here, you find that that fraction decreases in time. I think the mechanism responsible for this remains to be shown. You can imagine it might be a strong mechanism. For example, mergers of planets. If that were the case, then we would find that the overall abundance of multiple planet systems also decreases in time. We don't actually have that measurement yet. That remains to be made. You could also imagine a set of mechanisms that was more gentle and that manages to nudge planets out of resonance without totally disrupting the system. Those are also possible. Okay, so hopefully you will agree that stellar ages, especially for young stars, are beginning to teach us new things about how planets evolve. I'd like to spend the remainder of the time thinking about where this star-planet subfield is going. So in particular, what directions are going to help clarify the star-planet connection. And what I'll do is I'll highlight 3 that I think are related to one another. So the first is associated with where stellar age measurement is going. The second, where stellar activity, which is driven by age, is going. And then finally, where we're learning new things about how stellar environments interact with planets. So for stellar ages, what I'm really excited about is that we're learning that stellar rotation is really a remarkably good, in certain regimes, indicator for stellar age. So quick show of hands, actually. Who here has seen a plot like this before? Okay, this is about maybe a third of the room, so less than half, which means the majority of us can learn something new here. So what I'm showing is photometric rotation periods that have been measured from light curves from space-based telescopes and from the ground. So these are like exquisite measurements, right? Because the signals are really big relative to what these instruments were designed to do. And broadly, what's observed is that for stars in the youngest open clusters, the stars spin fast, right? The sun, for example, would have been spinning at maybe 10 times its current rotation rate at an age of 100 million years. Then, as stars age, they spin down. Okay? Now, what this means for age dating is that if you can measure photometric rotation periods for a star, then you can infer an age through interpolation. Okay, a star over here is older than 1 billion years old, younger than 2.6 billion years old. And you can actually be more precise than that. The intrinsic scatter in these calibration sequences is what sets the limiting precision for the method. So if that's 1 sigma, then this star would be 1, 2, 3 sigma older than 1 billion years. The K-dwarfs are doing something funny, right? Sun-like stars actually follow this magnetic braking Skumanich spin down, roughly rotation period increases as the square root of age pretty nicely. K-dwarfs stall. Okay, I'll talk a little bit about why in a bit. The implication for age dating is that you're not going to get a precise age in this regime, right? Because the rotation period is not diagnostic of the age. The relevance of this for the broad project of planet-star connections is that by measuring ages for larger samples of exoplanet host stars, we're going to be able to piece together this timeline a little bit better. Okay, so that's stellar ages. I want to talk a little bit about the connection between age, activity, and environment. So let's talk about activity. What is a magnetic dynamo? A dynamo converts from kinetic energy to magnetic energy. That magnetic energy can then heat various parts of the star, the corona, the chromosphere, and those emit in X-rays, extreme ultraviolet, and you can also kinetically excite particles in the solar wind. If the story were only that a dynamo converts from kinetic energy into magnetic energy, then you would expect in any plot of an activity indicator, this is X-ray emission versus something like the rotation period, that it would be a linear correlation the entire time. Or, this is linear and log-log. Instead, there's a saturation. Okay, the reasons for that are connected to how the dynamo self-quenches. But the point that I want to highlight here, since this saturation has been known about for a while, is that people are actually going much deeper than this dichotomy between saturated and unsaturated stars in the activity regime now. We're studying intermediate areas, and also for stars at the age of the sun and older, people argue that this paradigm breaks down in a different, interesting way. In the interest of time, I think one thing that I'll highlight, we'll skip stalled K-dwarfs. There's a lovely explanation. You should check out this paper. One thing that I'll highlight, though, is that if you look at any of these activity indicators and how they evolve in time, they have the same broken power law functional form. And if you want to understand that, it all ties back to how the dynamo is driven by rotation and also convection inside the star. Okay, so rotation drives activity and therefore environment, and the environment influences exoplanet outcomes. For close-in planet demographics, this is the case with basically any boundary that you'll see in properties of planets as a function of their parameters. But I want to focus on just one specific process in the time that remains, and that's atmospheric escape. So it's been known for a while that we can study atmospheric escape of exoplanets. Hydrogen was the original game. Lyman alpha has this huge cross-section. So you can measure for a planet with a 1% transit depth, a 50% Lyman alpha transit, because the outflow is overflowing the Roche lobe of the planet and it blocks most of the star. However, stars aren't very bright in the ultraviolet, at least most of them. And you need a spectrograph in space. An easier game to play from the ground is to look at helium. So helium 10830, we've heard a little bit about already. This is another tracer of atmospheric escape. Measurements like this can similarly demonstrate that a planet is overflowing its Roche lobe. based on comparison between the observed broadband transit depth and what you see in the narrow band. Something like 20 planets have this type of measurement. Maybe 50 have non-detections now. And what I'm excited about for this subfield is the prospects for taking those measurements in order to learn about how stellar winds interact with planets, in particular, planet magnetic fields. So what I'm showing here is a planet without a magnetic field, and we're just tuning the stellar wind strength between a regime in which radiation pressure drives a comet-like outflow on the right, and on the left, where the pressure is sufficiently low that you instead have a plasma torus that piles up around the star. I think for this type of effort to be successful, for us to really learn new things about star-planet interactions through doing this, the observations and the models need to advance in lockstep with each other. So what I'm showing here is an example of a 3D MHD model that was made for the system in the top left. And as an example of the type of process that you can study in exoplanet systems that in the solar system would be very hard to study, this is a planet that's on a polar orbit around its star. And we know that stellar winds have fast and slow regimes. So because of that orbital configuration, the planet is constantly going into and out of these different flow regimes of the stellar wind. I think that the observational connection between what that is doing in the data and what the models would predict isn't yet seen, but it's an example of where this subfield is going. So really quickly, tying it back to the solar system, I think that the solar system, in terms of atmospheric escape, really provides a basis for what kinds of physical processes can matter, right? All the terrestrial planets and some of the moons are undergoing atmospheric escape. Earth, as one example, has the geocorona. This is a sphere of hydrogen around the Earth. These particular images were taken in the 80s. Last Wednesday, a geocorona imaging observatory called Caruthers launched, and it's going to take way better pictures of Earth's geocorona in order to study how it responds to the solar wind. On Mars and on Venus, currently the escape of hydrogen is largely dominated by non-thermal processes. But I think the connection to the exoplanet science is especially strong at the earliest stages, when we ask the question of what did the primordial atmospheres of these rocky planets look like, and how did they produce what we see today? So the point is that the exoplaneteers have things to learn from the solar scientists, and vice versa. Okay, consider them at time. So I will leave you with my conclusion slide and the mantra: know thy star, know thy planet. Thank you.
Great talk. So first, I want the next speaker please come up so we can get mic'd up. And then question there. Yeah.
Why are stalled K-dwarfs anomalously active?
Thank you, Kevin. So let's imagine a star has a convective interior, or a convective envelope, and a radiative interior, and that those two zones can rotate at different rates. If the magnetic wind only spins down the top of the star, then you could actually decouple those two. Okay. At the era of maximal decoupling, you would expect there to be a lot of shear at the interface between them. That shear would generate strong activity, like, say, really large spot-filling fractions. That is what was measured in Lyra Cow's work. Basically, that the K-dwarfs that are stalled, that have rotation periods that don't seem to be increasing, are in what's thought to be a recoupling era, where basically due to stresses between the radiative interior and the convective envelope, the stars are in the process of eventually spinning down, but really they're only spinning down on the inside where we can't see it. Thanks for the question.
Great. Okay, I know there's a lot of questions, but we really only have time for one quick question. Do we have a quick question? Okay, maybe Ilaria?
We'll try to give a quick answer.
Yeah, thank you.
All right, thank you very much for the nice talk. I was just wondering if you can elaborate on the accuracy to which you can measure the masses of these puffy mini Neptunes, the accuracy of the mass.
The accuracy with which we can measure masses of mini Neptunes. Well, I presume you mean from transmission spectroscopy? It's degenerate with the assumption of the mean molecular weight of the atmosphere. So I personally treat it more as an upper limit than as a direct mass measurement, because you know that the mean molecular weight needs to be more than hydrogen. But if you make an assumption about the mean molecular weight, then people quote precisions of order 20%.
Okay, great. I know there are a lot more questions, so please, we are encouraged to use Slack, or please find Luke afterwards. So let's thank Luke again.